Okay, but what we should do is start it off with our equation. Get an equation down. Hopefully you remember how to deal with all the balancing and predicting formulas, all that fun stuff. Notice that I left off all the phases. Why? Yeah, for solving this question, it doesn't matter what the phase is. I don't really care, so I'm not going to worry about it. Okay. Also, I hate specifying phases, so I also just leave them off for that reason. I then want to include the information I know about each of those species underneath it. Okay. And I just realized that because I've got colors, I'm going to go ahead and color coordinate on this. We've got our barium hydroxide, which I'll show as a purple value. We've got the mole volume, 165 milliliters, 0.200 moles per liter. Right. The last bit of information that we've got there is our equivalence point. Okay. The equivalence point is when all of our acid has been reacted. Okay. Everything's been completely reacted out. So whatever was going to react has reacted. Anything I add beyond that isn't doing anything. Okay, so that's kind of an important aspect to realize. If I want to know the molarity of the nitric acid, I need to know the moles per liter of solution, and it would be the liters of solution of our nitric acid. That's why I'm trying to keep that one color-coded in red. Okay. Do we know the moles of nitric acid? This would be going back to the information we've got. Do we know anything about the moles of nitric acid? No. Okay, so we can't use that. Do we know anything about the liters of the solution of our nitric acid? I'm hearing 745. What is the 745? Milliliters. We want liters. So those aren't the same thing, but why are you suggesting we look at the 745? We can convert milliliters into liters. Okay. Where do I want that milliliter unit to show up? In the denominator, because when we look at our final answer, where's the volume show up? In the denominator. So I will start off my calculation. I'm going to attempt to do this as a straight line. With 745 milliliters of our nitric acid solution. I want to get that into liters. So my milliliters needs to cancel, and I need liters to show up on the bottom. What is the conversion factor between milliliters and liters?
1,000 milliliters in a liter.
Okay, all sorts of numbers come out of this. As long as you use it consistently and appropriately, I'm okay with it. My consistent method is to put the power of 10 always in front of our base unit. Our base unit for volume is the liter measurement. Milli means 10 to the minus 3. Okay? I now have liters of solution that I want for my final answer, and I have it in the proper space, the denominator. What do I want on top? Moles of nitric acid. Now we run into an interesting dilemma here. Do I have moles of nitric acid given anywhere? No. Okay? So I'm going to have to do some kind of conversion factor. Ideally, I would have moles of nitric acid up on top. Okay? I don't have that exact value, so I'm going to have to somehow find out where I can get it converted from. Can I relate the moles of nitric acid to anything else? This is just in general. Do we have any information in our given information that allows us to relate nitric acid to anything else? It's going to be related to our barium hydroxide. Not the volume necessarily of our barium hydroxide, because the volume of barium hydroxide has nothing to do necessarily with our nitric acid. Where does nitric acid and barium hydroxide show up? In the equation. Right? In the balanced chemical equation. That's where they show up. So I will use my balanced chemical equation to relate the moles of nitric acid to the moles of barium hydroxide. Hate this part. Thanks.
Yeah, comparing the two different ones always is confusing. That's where I miss it.
So yeah, as soon as you try and convert a different substance, you can only use, at this stage, you will only end up using moles as your conversion unit, and it needs to come from a balanced equation. What numbers need to show up in front of that conversion factor? 2 and 1. Where should the 2 show up? I don't like on the top. with nitric acid because there's a 2 in front of nitric acid in our balanced equation. That's why the 2 shows up there. What shows up on the bottom? 1, because what shows up in front of the barium hydroxide? It's an implied 1. Okay? If it was anything other than 1, greater than 1, we'd write it down. If it was anything less than 1, we wouldn't write barium hydroxide, because then it's not there. Make sense? What do we have for a unit now? Yeah, we have a lot. We have moles of nitric acid per moles of barium hydroxide per liter. Okay? That's not what I want for an answer. I need to get rid of my moles of barium hydroxide, okay? Which means I need to do another conversion. Okay? Ideally, I want moles of barium hydroxide to appear on top. Am I given the moles of barium hydroxide? Okay. Unfortunately not. But does that unit show up in the given information? We do see that unit show up in this value. Okay. What is that value? It's our molarity. It's a conversion factor allowing us to convert the moles of barium hydroxide to the solution of our barium hydroxide. Whoops. One of the things that can be confusing here is that if we look really carefully, you'll notice that solution shows up here, and I wrote solution in the product. Are those the same solution? No. Okay, this is why I tried to color code to help accent this. Okay. The purple solution is of our barium hydroxide. The red solution is of nitric acid. Those are 2 different volumes. They're measuring different species. Okay. What numbers need to show up now in that conversion between our moles of barium hydroxide and the liters of that solution? It's 0.2. There's a decimal spot there. Oh, you did say 0.2? Okay. We have 0.200 moles of barium hydroxide is equivalent to 1 liter of our solution. So this is nice. We do actually simplify our calculation here a little bit. Remember, our milliliters cancel. We have moles of barium hydroxide now canceling, but what's our final unit now? Moles of nitric acid per liters of nitric acid solution per liters of barium hydroxide solution. Is that the answer we want? No, we need to get rid of that liters of barium hydroxide. So we would have to do another conversion factor or another calculation where we have liters of solution, in this case of our purple solution. Am I given that information? I'm given milliliters, not liters. So what could I do? I can do a conversion between liters and milliliters. 10 to the minus 3 liters is 1 milliliter. Now if we go through and look at our units, I'd have milliliters of solution. I need the milliliters of solution to cancel. Okay. Am I given milliliters of solution? Yep. 165. What shows up in the denominator? 1. If it is anything other than 1, as far as a number, it's no longer 165. If it has any unit associated with it, it's no longer milliliters of solution. Okay. We track our calculation all the way through. What's our final unit? We've now set it up in one big, long, straight line calculation, and we have our final answer. Before we go randomly punching into the, well, not randomly, you at least know numerator, denominator, can we make any simplifications? Our milliliter-liter conversions cancel each other out, so we don't have to deal with the 10 to the minus 3. Okay? So we can remove that calculation from doing it in our calculator. We can now punch it in the calculator and we end up with a final answer. Kind of make sense? Questions about that? As far as the level of difficulty of this kind of question goes, this is not final exam material. Okay? What you're expected to do is to be able to interpret molarity, not be able to interpret molarity and equations at the same time. Okay? Kind of make sense? Okay. So, nitric acid and barium hydroxide are interesting reagents because they are acids and bases. So what happens if we mix an acid and a base? We get a neutralization reaction. Right? Why do we go through and name neutralization reactions and in fact go through and name these compounds? Add this extra term of acids to our name. Why has that become important? Two beakers with clear liquids inside of them. One says acid on it, one says water. If you are told to drink one, which one do you drink?
Water.
Water. Why are you not drinking the acid?
That's no good.
That's no good. We are trained to realize that certain chemicals are particularly reactive. Acids and bases just happen to be one of the first kind of bulk classifications of chemicals that came about historically. So we name them kind of more importantly than everything else. Because we always need practice with nomenclature, how about you name these compounds? The last one is sulfuric acid. How do you know to call it sulfuric acid? We have the H out front and it says aqueous. Both those terms together get us the acid aspect of this. Okay. Why do we not specify the hydrogen in the name? The ick is in reference to this being sulfate. Okay. Because we ate too much, we became ick. That's all I got. And actually, that's not mine. Okay. So if we look at the name of our complex ion, we can use the ending of that to determine what kind of ending we get in the acid. Okay? But again, why do we not say hydro? Nope. I go through and drop in aqueous off that first one. The name of that compound becomes? It is hydrosulfuric acid. Why is the first one hydrosulfuric acid and the last one only sulfuric acid? Kind of back to the oxygen. It's a ternary acid. Ternary acids, we do not specify the hydrogen. Okay? If it's a binary acid, only two elements, we need the hydrogen, or we need the hydro specified. Okay? So the easy answer to that question was, why do we have two different names? That's the hard answer, which is correct. They're two different compounds. If we named all of our compounds Bob, that would get a little bit silly when looking at a reaction. Bob plus Bob gives me Bob. What the hell happened?
Science.
Okay. Good timing. Okay. We need some kind of nomenclature system that allows us to distinguish those compounds. Okay. Now what happens to the name? As soon as I get rid of that AQ, it's no longer an acid as far as our nomenclature rules go because we don't have the AQ. What type of bond do we have? A covalent bond. What are our rules on covalent bonds?
Dihydrogen sulfide. Monosulfide.
Dihydrogen, and the mono can be implied sulfide. There are all sorts of common names that can come out of this, but that's our full official name. Middle one? So I heard a sulfate. That's good. Dihydrogen sulfate. Okay, why do we need the di? It's kind of a weird gray area one. It is still officially all sort of covalent bonds, which is why we're using the dihydrogen. Okay, we could probably get away with just calling it hydrogen sulfate as long as we did not call it hydrogen sulfate ion. The instant we throw in the ion, we're referring to HSO4 minus. Okay. For those of you that have done the practice exam, that might jog some memory because that was a question straight out of the practice exam. Okay. So, is that a question? Oh, thank God. I just deleted everything. Okay. So why does sulfuric acid get a different name? Okay. This, again, comes back to what we've been talking about, or how we address this to begin with. Okay. Our acids and bases carried very particular chemistries that happen to be particularly dangerous, and so we invented names so that we could then say that's an acid and nobody drinks it. Okay? Kind of as simple as that. Some observationalists came through and observed some characteristics of these. You'll notice that one of the very first observations is looking at how it tastes. So the guy drinks it and dies, but as he's dying, he says, "Oh, that was sour." Sweet. We've got some information. Okay. The other one tastes bitter. Okay. Different reactions with our tongue, which would suggest a different type of compound. The other thing we could go through and do, slightly less dangerous, but still kind of bad, is touch. Okay. We rub one of those on our hands, then it starts to feel sticky. We rub the other one on our hands, it starts to feel slippery. We're getting some pretty drastic, different observations from these individual chemicals. I don't remember, did I actually? Sort of did. Turns out the ones that are sour tasting and sticky feeling tend to be acids. The ones that are bitter tasting and slippery feeling are bases. You know the Sour Patch Kids, right? Those kind of candies. Why are they sour tasting? Citric what? Citric acid. There's an acid component to those. So not all acids are toxic and going to kill you. Okay? Some of them are relatively benign and kind of fun to taste because they get us a different flavor profile. Okay? What happens when we move into our bases? Okay, where have we used bases very commonly? Hopefully multiple times today already. Soap. And soap is slippery feeling. Okay? And that has to do with the properties of our soap and how it separates things. Okay? So if we look at our overall reaction of mixing an acid with a base, what happens? What type of reaction? A double replacement, which is unfortunately better named something else. Neutralization. Why do we have to add that extra term? Because acids and bases were our first thing discovered. Okay, that's our origin on it. So we kind of have to run with those. One of the advantages to calling it a neutralization is for the sake of this class, all neutralizations will produce water. So if you can identify it's a neutralization, you already know one product. After that, whatever pieces didn't make water, put together. Okay? Since it's a multiple choice exam, you don't even have to worry about the order in which you put it together because we're not going to test you on that. Okay? So all you've got to do is say, well, I need sodium and this weird C2H3O2 thing hanging out near each other. Oh, the sodium's first? Okay, there's my answer. Okay? Kind of makes sense? It's a very good way to do it. Okay. First definition that came about was a guy named Arrhenius. Really, really, really old and really, really, really dead. And what he noticed is that when he put an acid into water, he noticed that there was an increase in the concentration of hydrogen ions. So he said, okay, well, if hydrogen ions go up when I put an acid into water, I'm going to now name or define my acid as a species that produces hydrogen ion. That's it. Okay? And now we have to name a stupid definition after him. Thank you very much for making such a dumb observation. Okay? And now we have to remember your name. Right? What happens when he takes bases and he adds them to water? He says, oh, well, the hydroxide ion increases. Did he do anything with it? No, it increased. And now what do? We name our acids and bases after that guy for that discovery. Science, yeah. Okay. So a lot of scientific discoveries are very basic observations, but they got done first, or most intelligently first, and then reported, and then their name gets rubber stamped to it. That said, I personally think this definition is useless. Okay? Largely because the definition doesn't apply to enough chemistry. When we're looking at our reactions, we want a definition that can apply to everything when I do a reaction. I don't want to say, well, in this particular case, this is this type of reaction. And in this particular case, it is this type of reaction. Because then what are we responsible for doing? Memorizing all of these particular cases and all of their particular results. That gets a bit tedious. We want a definition that is broader and allows us to apply to multiple situations. Okay? So a little bit later, we came up with a better definition between two guys, Bronsted and Lowry. In fact, actually, if you get really fancy, I think it's Bronsted. There's some fancy umlauts and things like that in his name. Okay? When he went through and looked at these, he said, okay, yes, we're producing hydrogen ions, and yes, we're producing hydroxide ions, but I want to focus on what I think is the most reactive thing present. And so what he decided to focus on was the hydrogen ion. Okay? Much like we've done naturally in society. Okay? You are conditioned to think what is more dangerous, acid or base? Acid. Is it more dangerous? No, they are equally dangerous. Okay? There's not one more dangerous than the other. Okay? But for some reason, I still don't understand why, we are trained to think acids are more dangerous. So he stuck with the acid definition. Said, this is the one that we're going to work with. I'm going to focus on the hydrogen ion. So he's still going to call an acid a hydrogen ion donor. So when we go back and look at our compound up here, HCl, what does it look most like in the product? I know it's a little bit of a hard question. NaCl. What happened to that compound in the course of the reaction? It lost hydrogen. Okay? Or it donated that hydrogen to another species. That's how we get our definition of an acid, a hydrogen ion donor. So we're comparing across our reaction, just saying what things changed. Okay, now I'm going to define my reaction based on that change. Okay. What happened to the base? Our base being hydroxide, well, that's naturally then going to say it's becoming H2O as our partner. What happened to it to become H2O? It accepted a hydrogen. Okay. Yes, it produced hydroxide, and that hydroxide reacted with the acid of H+, but we're still looking at defining it based off of the exchange of the hydrogen ion. Okay. And so the definition we end up using for our base under the Bronsted-Lowry definition is we have a hydrogen ion acceptor. Right? So we use our equations, we make some rough comparisons across that equation, and then stamp our name on top of it as saying we are now fancy and cool because we made a better observation. Okay? This is a useful definition, though it is still very, very limited because it requires that what happens.
There's a reaction.
Yes. Yes. Requires the transfer of a hydrogen. Do all reactions transfer a hydrogen ion? No. So while this is a broader definition and it applies to slightly more reactions than the Arrhenius definition, it's still not the best. Okay? If you move further into chemistry, that's when we'll evaluate the best definition. And I think I may have left it off the slide, so if it shows up, we'll worry about it then. Okay? So now into this concept of our conjugate acids and bases. So we're going to look at a reaction and say, okay, what happened? We want to predict what's going on with these. Right away when we look at these, we should be saying something looks a little bit odd about the reactions I've got shown up here. What is that something odd? Holy crap. So there's a lot of things odd about it. Okay. You'll notice that we have two arrows. One going to the right, one going to the left. What does that suggest? The products can react with themselves to reverse the reaction, to make our reactants. Everything we've looked at so far this semester says the direction of our reaction always goes left to right. We only form products. We never look or think about the reverse. The reverse is always something we have to be concerned about. Okay? What else is odd about it? Okay, in the very first equation, they both have hydrogens. Okay, that becomes tricky. What else? When we looked at our reactions before, what are the charges on all of our species? 0. They're always neutral. Do our reactions always have to have neutral reactants and products? No. Depending on what we're looking at, we may end up generating charges through the course of the reaction. Okay? So both of these start with charges, and the intent there is to help accent and help you identify what type of chemistry is happening. I would argue that the bottom case is going to be the easiest example to look at. So let's start there. Okay, we're looking at acids and bases, so this is likely going to be a neutralization reaction, right? What would we expect SO3 minus 2 to act as? Why can't it act as an acid? Definition of an acid is hydrogen donor. Does it have hydrogen? No. So if it's not donating a hydrogen, it had better be a hydrogen acceptor. So let's have it accept a single hydrogen. Okay, and this is one of our cases. We're now stepping our reactions as opposed to just full-on shotgunning it across. Okay? So we want that species to accept a hydrogen to produce the product. What would it look like? Does everybody agree? I heard a no. What's the no? What about the charge? Right? We only accepted one hydrogen, and the hydrogen's coming in as H+. If that started as a -2 and I accept one positive charge, the charge needs to become -1. Okay? And I think what you were then hinting at was the next part, which is
H2O.
What's the other product? H2O. Okay, what should the charge be on our H2O? Okay. H3O plus is positively charged. What do we end up losing? What is that species? What happens to that species? It loses H plus. If it loses a positive charge, it becomes, it would start to become negative, but since it started positive, it becomes neutral. Okay. So we're looking at the balance again of our charges within our molecules and how that translates out. Questions about that? Okay. We already actually started to define some of these species. We said the SO3 minus 2 is likely going to act as the base, which then meant the H3O plus acts as the acid. That's going from left to right in our reaction. I want to go right to left now. So I go from right to left. What happens to HSO3 minus? So I'm starting with HSO3 minus, and I now want to go to SO3 minus 2. What happened to it? It donates a hydrogen, which then means that species is acting as color coding. What happened to H2O? It had to accept a hydrogen, and accepting a hydrogen is defined as a base. Okay, and actually I'm going to rewrite those in just a second here. Okay, so now the next fun question. What species is the acid? Don't all shout out an answer right at once. Is there a reason you're hanging on that word, not trying to give me an answer? Which species is the acid? Did we not just define what the acid was, right? Donates a proton, right? Go ahead, speak up. HSO3 minus is defined as an acid. Hence, we wrote underneath it, acid. What's the but? There's another species that's an acid, H3O plus. So if I ask the question, what's the acid? Well, it's one of those two. Which one?
The reactant side.
We want to be a little bit more careful within our referencing of what these things mean. So I want to add an extra term to this to help me identify so that when I ask the question acid, you know that I'm referencing the reactant side. Okay. And in general, that's what we mean. Okay, so how can I refer to the acid on the product side then? That one is not quite good enough. Okay, we add a new term. That new term is the conjugate acid or the conjugate base. Okay. Where are our conjugate partners? What is the conjugate partner to HSO3 minus? SO3 minus 2. Our conjugate partner to H2O? H3O plus. They're the two species most related to each other across the reaction. Those end up becoming our conjugate partners. This is how I want you to understand these definitions and these terms. That said, I then have to add the caveat, okay, which hopefully becomes somewhat obvious of a reference here, that perhaps near in the future you're going to have to use these terms and understand what they mean, and they are inappropriately being used to mean conjugate, referencing both sides of the equation. Okay. Anybody get the loose reference there? The near future, you might need to know this definition. Final exam.
Yeah.
So now that you got an idea on our conjugates, on how to label them, I want you to go through and do that top equation. Okay. Identify your acid, your base, your conjugate base, and show the arrows connecting which ones are conjugate partners with each other. And coming from an organic chemist that seems to understand acids and bases better than general chemists do, your conjugate should only reference the product side. Okay. Just a second. Let's pause the. I did not tell you anything of the sort. I haven't got a haircut. What the heck? If we go through and look at this particular reaction, what did our HSO3 minus act as in this case? The acid donates a hydrogen to our water. We end up forming SO3 minus 2 because we've lost H plus, so it becomes more negative. The water gained a hydrogen, which was positively charged, so it comes out as H3O plus. The other answer says what? Water acts as the acid, and HSO3 minus acts as the base. Okay? So when we look at this equation, there's two possible answers or two possible ways to predict because both of those species have hydrogen. We don't have the knowledge yet to be able to decide which one of those reactions is the correct reaction. Don't stress on that. We're just asking you to think about what's going on within those reactions. Kind of make sense? Okay. So double arrow. What the double arrow means is equilibrium. For those of you that have to move on into 152, you will learn to deeply loathe and hate equilibrium, particularly if you aren't particularly good with mathematics. 152 is all about equilibrium and the mathematics to support and calculate what's happening within that. Right? It is looking at the preference for which side of the reaction is favored. Do we expect more products to form or more reactants to form? Because with a reversible reaction, both are potentially happening. Right? So your equilibrium is just the balance of products and reactants. All reactions will go to achieve this balance. Okay? It's not saying that we have equal amounts of products and reactants. It's just saying that once we have achieved the equilibrium, the balance of how many products and how many reactants are present will stay constant. Okay? Once we are at this constant point, okay, of course, what do scientists then go through and do? Mess with it. Okay? We hit it and see what happens. Thank you, Mr. Le Chatelier. So once our reaction has achieved equilibrium, Le Chatelier says, okay, what happens if I now punch the reaction? What does it do? Okay? It responds by doing whatever it has to maintain equilibrium. Okay? So it will adjust the concentration of our reactants and products to ensure that that ratio is perfectly obtained. There are two kind of visual ways to interpret this. We can look at it as a seesaw, and we can look at it as two divided chambers. Okay, we'll start with the divided chamber aspect because I think that one's a little bit more straightforward. If we go through and look at our chambers, one side of those chambers we'll call our reactant, the other side we'll call our product. Okay, and what we're going to do to start off the reaction is we will put a wall up between the reactants and the products so that they cannot interact with each other. Okay? And now I'm going to put in a bunch of reactants. Pretend our reactants are just a liquid, say water. So I fill up the reactant side of this chamber. Okay. Now I tell the reactants, okay, now you can become products. Do whatever you got to do to become products. To do that, I have to erase the barrier between them, and now what happens? The liquid level falls because it's moving over to fill the product side. When I have achieved equilibrium, what's happened? They are both at the same height. We have the same amount of reactants and products present in both. This does not mean water is no longer traveling over to the product side, and it does not mean whatever's on the product side isn't moving over to the reactant. What we're saying is that the amount moving to the product is the same as the amount moving to the reactant. Yes? So now the question is, we're at equilibrium. So Le Chatelier says, okay, I want to mess with this. So he's going to say, reaction, stop. Barrier, can't react anymore. Stop it. Okay, now I want to mess with it, and I'm going to say, you know what, my messing conditions is I'm going to add some more reactants. Now I say, okay, reaction, go. What happens? It's going to try and re-achieve equilibrium by balancing out the amount of liquids on each side. Our reactant value goes down and our product value goes up until we have achieved our new equilibrium.
So you have to add something.
And that punching it that I used before as a poor description is either adding something or taking it away. What happens if I've achieved my new equilibrium and I now say reaction stop? I should do that in black because I've been doing that. And now I'm going to say I want to remove some of my product. Now I say reaction go. What happens? The reactant side will drop and the product side will go up until I have achieved my new equilibrium. Okay? So I can add or remove. Depending on where I add or where I remove, I'm going to get slightly different responses. Okay? For instance, in this case, both cases we end up seeing an increase in the product. What could I do to see a decrease in the amount of product present? How about I take away from the reactant side? If I drop the reactant side lower, when the reaction is now allowed to start again, what happens? the product side goes down. Somebody else started to suggest something else before I started drawing that one. Add to the products. What happens if I put more products in? Okay. We're going to have to go down to re-achieve that equilibrium. One of the issues with this model is that we then assume what is the amount of reactant and product at equilibrium? Equal. That's not true. Okay. How can we change this model to better represent that?
The next model.
The next model, I think, is better at doing it. But the other option, change the size of the well you're working within. If the reactant line is now set up as such, when I put the reactants in, what happens when I now allow the reaction to go?
It's barely going to fill the products.
It's barely going to fill the products. We're going to see an imbalance between those two layers of having slightly more reactants than products because of all sorts of complex things like surface tension and all that fun stuff, which I think makes that example start to fall apart. Okay, so let's move to the seesaw. Okay, the seesaw, I think, is a little bit cleaner to look at. We'll use a reactant as a box representing its concentration, our product as another box representing its concentration. The equilibrium is going to be the fulcrum on our seesaw, the middle point. Okay? So if we stick with the kind of example that we used with the first one, let's put our fulcrum close enough to right in the middle. What happens to achieve equilibrium? What should the concentration be of both reactants and products? The same. So I would expect roughly the same size box on each side. What happens if I now, as Le Chatelier, go through and add more product? Okay. Immediately it shifts out of balance. It needs to reattain balance by doing what? We will cut a section of our product out, and we will make that reactant. We can't just add more reactant, because remember, the reaction doesn't have access to more stuff. It has to come from the reaction itself. So if I add product to it, how do I increase the reactant? I need to take away that product and turn it into a reactant. That's what the reaction is doing. In this example, what's the concentration of reactant and product at equilibrium? The same. I have to have the exact same amount on both sides because where's equilibrium? Established right in the middle. What happens if I move the fulcrum? If I put the fulcrum now over here, okay, what is my equilibrium going to show? Should I have the exact same amount of products and reactants? No, because then the product would overweigh and it would tilt. So what do I need to do? I need a lot, whoops, oh no, I did that right. A lot more reactants than I do of the products. So, well, why do I care about equilibrium? When you go into chemistry, the whole point of chemistry is to do something. What is that something we're trying to do?
Turn lead to gold.
Lead to gold. We're trying to make something. That is our goal, to make a product. If I look at an equilibrium for a reaction and I can establish and figure out where that fulcrum is located, is this a good reaction for me to do? You're shaking your head no. Why? Our goal is to make product. How much product do I make by running this reaction? None of it. Okay? That's a really crappy reaction to run. Equilibrium allows us to look at it and say, that's a good reaction because I'm going to get lots of product. Or, holy crap, that's an awful reaction. I don't want to touch that reaction because I'm not going to get any product. Where should I put the fulcrum to ensure that I get the most product for an individual reaction? Okay, I heard the center. What happens if I move to the center? I have equal amounts on both sides. Can we get better? We want our equilibrium as far to the right as possible, which means I need a lot of product to counterbalance the tiny weight of the reactant. Okay? And for those of you going, wow, this is way too difficult, I can't even understand what's going on with this, 152 puts in all the exponents, powers of 10, and calculations behind it so that you can look at the mathematics that support this.
You
Okay?
don't have to do the mathematics.
You are not responsible for the mathematics, and in fact, when it comes to equilibrium, kind of what you're responsible for doing is acknowledging what things are going to change it out of equilibrium.
How does that work with conservation of mass?
Conservation of mass just says the mass has to be the same on both sides of the equation. We can change the concentration of each by changing the number of molecules. Concentration is the number, not the mass. Okay. Questions? I actually have a better answer to that, but I can tell you after class. Why? Because it's not super relevant for the question or for the exam. So, equilibrium and acids. Okay? Could we use this to describe the reactivity of an individual acid? So we just looked at two potential equations. We had HSO3 minus reacting with H2O to produce H2SO3 plus H3O plus versus the other equation, which was HSO3 minus plus H2O to get you SO3 minus 2 plus H3O plus. Okay. And what we were deciding is, well, which of those reactions is more likely to occur? Because both of those are possible. Well, what we could do is look up the equilibrium expression for those. Well, the equilibrium expression is looking at the balance of the products to the reactants. Okay. When we take a look at this first expression, or that first value, what we end up finding out is that the concentration, or our K value, because you'll love that when you get there, capital K is our equilibrium, is products over reactants. What we end up finding out is for the equation I showed on the left, that equation has a K value that is incredibly small. And for the one on the right, our K value is incredibly large. What does that mean?
It's a good reaction.
Which is a good reaction?
Small on the left and large on the right. Oh, no, it's equal because the thing is equal.
Remember, your K is calculated by looking at the products over your reactants. If we have a large K value, what does that mean? More products than we have reactants. What does that suggest? It was a good reaction. We had lots and lots of products formed. Which of our little seesaws would line up with that? Okay. The one on the right will match with that, because I need a very small mass of my reactants. The right side has to weigh that out, and because it has less of a leverage effect from physics, we end up seeing that effect. Hey, look at that, I drew it under the appropriate reaction. Okay? So what we're trying to understand is how basic changes in our reaction can turn into drastic changes in what we perceive and the predictability of those reactions. Okay? Really important concept, difficult to interpret, work with it the best we can. Okay? Is that a question? What's that? Oh yeah, we definitely needed hydroxide there. Sorry. Yeah, so one on the left was hydroxide. Sorry. Okay? So, let's let that go. Strong versus weak. Okay? This comes up with our concept of electrolytes. And I believe you're welcome, because the lab you're doing this week is electrolytes. Hey, look at that. I timed it beautifully. Okay. What do you mean you already did it?
You did it Tuesday.
Yeah, Tuesday.
Oh, today's Thursday, huh? Yeah, so close. So close. So close.
Thursday, lad. Don't forget about that.
Thursday lab. Hey, I did this for you. Okay. When we're looking at our reactions, deciding on our ions and what can happen within them, strong acids and bases, when they hit water, completely ionize. So they completely shift to forming our products. They have massive K values, okay? Really, 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 really big, okay? And what that ends up generating are ions in solution. Okay, well, what are ions? Charges. What is electricity? Charge. If I take a material that has charge in it, what are the odds that I'm going to be able to pass charge through it? Pretty high. So what ends up happening? I have a material that can pass charge. Okay? If that charge happens to be hooked up to, say, a light bulb, I can say I'm passing electricity, electro, to power a light. Come on. And we have an electrolyte. Okay? We're looking for the passage of charge through a solution. Our weak acids and bases don't ionize as well. So when we put them into solution, we don't get those charged species. If we don't have charge in our solution, can we pass electricity or charge through it? No. Okay? We need to have charge present to allow charge to pass. Okay? So, our varying extents for our weak acids and bases, you get a lot of in 152. How do we know the difference between our strong versus our weak? Well, the strong acids are shown up here. We have the first one known as? Close. Perchloric acid, followed by? We just named this one. Sulfuric acid. Maybe in 2 weeks. Hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. Our strong bases are anything with hydroxide and group 1 and 2A metals. Okay? There are some loose exceptions in there, but for the most part, those are our strong acids and bases. Well, what are our weak acids and bases then? Everything else. Okay? So when it comes to but knowing which one you're looking at, you're responsible for knowing the strong acids. The weak acids and bases you're responsible for knowing because they aren't the ones that you've memorized as strong acids and bases. When it comes to actual memorization for this test, I don't think you need to know the specific strong acids and bases. You will need to know it for 151 if you have to advance. Okay. Make sense? Ish? Yeah. Kind of feel like I've broken you. Okay. Think about safety. Okay. If we shout to our little Timmy here, hey, watch out for that 0.15 molar H plus solution, it'll burn you.
Yeah, Timmy's a goner already.
Timmy's going to be, what the hell are you talking about? Decimal values. What is this molar? Okay, what is H plus?
Why is Timmy hanging around?
We don't want to be throwing all of that information at it.
Where's his parents?
We want to be able to come up with, you're his parent. We want to come up with another way to represent the concentration of hydrogen ion, because that's dangerous. If we have a large concentration of hydrogen ion, we have something that's very acidic. So what do we tell Timmy to watch out for? Did you say facids? Because facids was going to be a little bit more appropriate.
Oh, come on. You should have let me have it.
We'll reference pH systems. Okay? How do we determine a pH, or how do we use pH?
Water.
Water is what pH? 7. Okay? We then can say our acids are very low pHs, and our bases are very high pHs. So by now referencing and kind of getting an idea of what's happening, we can, instead of giving us this big long decimal system and molar and all of that, we can just say, well, 7 pH is neutral. Okay? Water, don't panic about it. But a really low pH, that's dangerous. Watch out for that. Or a really high pH, watch out for that. That's dangerous. And instead of dealing with decimals, our pH system runs off of what scale? 1 to 14. Okay, can it go lower? Technically, yes. Can it go higher? Technically, yes. Why do we stick with 0 to 14? Water. When we use water as a solvent, that is the range of pH possible in a water solution. Why do we look at water? That is our most abundant solvent. Okay? How do we calculate the pH? Well, this is another reason why people don't like chem152. You get to use a logarithm. You take the negative logarithm of the concentration of your hydrogen ion.
Why do you have to bring calculus in this?
Calculator does it for you.
It's not calculus.
Your calculator does it for you.
Yeah, 'cause
You don't need to know
calculus
what logarithms mean. Okay?
You should.
Largely because I still don't know that, and I feel kind of bad about that. Okay? But you do need to be able to use it. Okay? So you just take the logarithm of the concentration of hydrogen ion in your sample, and you now have the pH. Okay? That's it. If we go through and apply to electrolytes, okay? I know I'm pretty much done. I just want to get through this last slide. Okay? Anything that we add to water that completely ionizes, okay, is considered an electrolyte or a strong electrolyte. Okay? What it's allowing the passage of is electric current or electrons. We can do electrons through charged species. Which of these would we predict to be electrolytes? Why is sodium chloride a strong electrolyte? Metal and a non-metal, it ionizes. But if we look at silver bromide, isn't that a metal and a non-metal?
That's not good function.
Silver's an exception, nice sort of dodge. Silver bromide, according to solubility rules, is a solid. It's insoluble in water. If it's insoluble in water, it can't ionize. Okay? So we would have to use our solubility rules to also help us predict what's going on with these individual species and whether we generate ions or not. As a quick run through, those top three are all strong electrolytes. The middle are all non-electrolytes. Okay? The last one, we run into some weird kind of gray areas. We've got some weak electrolytes, and we have some non-electrolytes in there. Typically, for your rule of thumb, if you have something in a non-polar covalent system, non-electrolyte. Okay? And we'll end there. I apologize for running long.